Hello, class. Hopefully you are watching this on Thursday. I'm currently recording it on Tuesday. This is the section we're going to learn about circles and lines. So we'll do circles, this whole chapter of circles. It'll be circles and lines for 8-1. And we're still in neutral geometry with these circles. And we'll break into Euclidean geometry, I believe, in section 8-3. But we'll start with this. So if you want, by yourself, or if you're watching it with a friend or two, feel free to say it with me. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this: love your neighbor as yourself. There's no commandment greater than these. All right. With that, we are hopefully our minds are ready for mathematics and our hearts that are mostly at ease, hopefully, and we're ready to go. All right. So, I need to be able to draw. All right. So, definitions. So our definition of a circle is given a point O and a positive real number R. Circle with center O and radius R is defined to be the set of all points P such that the distance from O to P is R. And so you can call it this. So it is the circle centered at O with radius R is all these points P such that OP equals R. The number R is called the radius. We sometimes call the segment OP a radius as well. Sometimes radius is a number and sometimes it's a segment. Okay, and that's can't be helped. And then this notation C of OR is kind of clunky. So when we only just need to refer to a circle and not necessarily care about where the center of radius is, we might name it a Greek letter, and gamma, which is kind of that symbol, is going to be our favorite name for circles. Okay. Now, let's talk a little bit about our weird metrics and our current metric. So our weird metrics, say when we did like distance from x1, y1 to x2, y2, and that was, say, absolute value of x1 minus x2 plus absolute value of y1 minus y2. Well, then our circles then would have been like this, because all these points are, say, distance 1 from the origin at 0. And that's weird. So that's why we agreed to the axiom of SAS. And SAS makes it so our triangles have to be the same even when we rotate them, as long as they have that side angle side. And so that doesn't work in this, but it does work in Euclidean geometry, where we have perfect circles, and it works in hyperbolic geometry, where our circles can have a little bit of bend to them, depending how big or small they are. If they're really, really big, they can have some weird bend to them. Okay. Now, some more definitions. There's lots of definitions in this section because we're doing this whole circle thing creates a whole bunch of different things we need to name. So let gamma equals a circle. So let gamma be a circle centered at O with radius R. A chord, that's a new word, a chord of gamma is a segment joining 2 points of gamma. If the chord includes O, then the points on gamma are called the antipodal, and the chord is called the diameter. So antipodal is if they're on completely opposite sides and the chord includes the center. And if those points are on opposite sides, their line segment creates a diameter. So a point A such that, so let's just draw. So a normal chord is like that. A diameter will include the middle. And if you have a point A in here, where here's O, and if that distance is less than R, then it's called inside gamma. And so there's A. And then here's a point B. And if this distance is greater than R, then that's called, that B, point B is called outside the circle. Okay. Now, here's our first theorem of this section. If gamma is a circle and L is a line, then the number of points in gamma intersect L is 0, 1, or 2. So the easiest way to prove this, since we have to prove three things, we could do it by cases, or it's much simpler to do a proof by contradiction. So if we do a proof by contradiction, we might say, assume L intersect gamma includes at least 3 points, or just includes 3 points. 3 distinct points. Okay, now here's where the definition of a circle and our intuition of a circle can be different a little bit. And it's helpful to know that just like go back to the definition. So the definition of a circle is only distance. There's no sense of like the kind of a bent line or anything like that. And so if I say my original proof by contradiction is like, okay, well, assume a circle and assume I've got a line that goes kind of like there's my line. It hits 3 times. That's kind of ridiculous to draw. And so instead, think of I've got a line and I've got say named points A and B and C. I've got at least 3 distinct points, and they're all, here's O, the center of my circle. And I don't have to draw the circle. I just know that all of these are the same distance. Hence, they're congruent line segments. Hence, I have isosceles triangles. But these are a linear pair, and so that makes them 90 degrees, and they're isosceles, so that's 90 degrees. And all of a sudden, I've got triangles that have angles adding up to greater than 180. Contradiction. Okay. I could write it up, but I feel like that would be boring for you guys to watch. So that's kind of the main idea of the proof. Okay. Definition. Also, I don't have to write it up because if you're curious, I believe that this proof is in the book. So definition, a line L is tangent to a circle gamma if L intersects gamma in exactly 1 point. If P is the point at which L intersects gamma, then we say L is tangent to gamma at P. Okay, so a line can be tangent and a point can be the place where the line is tangent. Okay, for line segments, here's a circle. The line segment has to be the subset of the line where the point of tangency is included. Okay, now a line L is a secant line if it intersects in 2 distinct points. So in that case, you got 2 points there, right? So the line segment here, let's change colors. So that line segment there is called the chord of a circle, and the entire line is called the secant line. Okay. So now we have another theorem. Let T be a line and gamma be equal to C0R be a circle, and P is a point on the intersection. The line T is tangent to the circle gamma at the point P, if and only if OP is perpendicular to T. Okay. Well, we got to do, first we'll do this way. So the line T is tangent to the circle, if and only if OP is perpendicular to T. So assume you've got the assume the hypothesis. So in this case, like this that's the hypothesis. That's what I'm assuming. Assume the hypothesis. Okay. And that T is tangent to gamma at P. Tangent to gamma at P. All right. So we need to show that OP is perpendicular to T. Okay. So we've got gamma, center O. There's P. So there's O. There's P. And actually, let's just draw that. Oh, let's draw a little better. There we go. No, it's okay. All right, and that's P right there where it's tangent. And there's OP, the line. Okay. Then why don't we pick another point on T, maybe call it A. And what if this angle was not 90 degrees? Okay. If it was not 90 degrees, then it's either smaller or larger. So then rename A to be on the other side or whatever so that it's acute. Okay. So if it's acute, then why do you think it is going to be a contradiction? Never mind. Let's try this again. Okay. So again, we have our circle. O is there. P is there. Well, and then we've got OP. Well, we can always drop a perpendicular from O to the line T, right? So drop a perpendicular. There we go. Now, assume, let's call the point Q. So if we assume Q is not equal to P, then I can create the point, I can measure that distance and create the point on the other side of Q and call it R. And then I can do that. Well, then I've got this line is congruent to itself. So I've got SAS tells me these triangles are congruent because of side, angle, and side. Therefore, this is congruent to that. If that's congruent to that, then R has to be an element of gamma because it's the same distance from O as P is. And the definition of circle is all the points that are the same distance. However, that contradicts that P is tangent, because to be tangent, the line has to only intersect once. So this contradicts tangency. Okay. Now let's do the other side, the other direction. Okay. So here we go. Kind of erase this. I thought this might go faster than at first, but here we are. All right. Now the other direction. So assume the hypothesis. And assume OP is perpendicular to T. Well, if this is the case, then I can think of O being here, P being here, and there's that line segment, there's T, and it's perpendicular by our assumption. Then pick any other point on T not equal to P. Okay, so I pick pick Q element of T with Q not equal to P. Okay, well then OPQ is a triangle. It's a right triangle. Since it's a right triangle, that means that this angle is the 90-degree angle, and so the other two angles must be acute, since all angles add up to 180. Then that means that this side, OQ, has to be bigger than OP because it's opposite a bigger angle. So let me use a different color, orange. So this is the biggest angle, so it goes across the biggest side. This angle has to be smaller, and so it's going to be across, OP must be smaller than OQ by the Scalene triangle theorem. So recall, so by the Scalene triangle theorem, I hope I'm saying that right, by the Scalene triangle theorem, OP is less than OQ, therefore Q is not an element of gamma. Thus, P is the only point of T that's on P. Thus, P is the point of tangency of gamma and L. All right, now moving on. Now we've got theorems that are your homework. So theorem 818 says if gamma is a circle and T is a tangent line to gamma at P, then every point of T except for P is outside gamma. Well, I might have kind of given that away in the last proof, so you're welcome. And then theorem 819 is a secant line theorem. And so if gamma equals the circle center of the O and with the radius R, and you've got L as a secant line that intersects gamma at distinct points P and Q, then O lies in the perpendicular bisector of the chord PQ. And so the homework, that is also homework. And there's a particular theorem from chapter 4 that will help you out a lot there. And that's all I'm going to say about that, since I already gave you way too much for homework number 2. All right. So theorem 8110. If gamma is a circle and L is a secant line such that L intersects gamma at points P and Q, then every point on the interior of PQ is inside gamma and every point of L without PQ is outside gamma. So our theorem is claiming that there's P, there's Q. PQ is inside gamma, and then everything on L, not PQ, is outside gamma. Well, we can use the fact from theorem 819 that O lies on the perpendicular bisector of P and Q. And so then if we say, pick any other point in here, call that point R, then if I consider that why is R closer to O than, say, P or Q? And the reason is, if I form that little triangle there, then R is a part of a O, and then whatever this point is, OPQ, let's just call it A. OAR is a band that's saying Wonderwall, but also a triangle that has a right angle right here. And that triangle makes that, since that triangle is a right triangle, that makes that angle acute, which makes this angle obtuse, which makes this the longer side, which makes then of this triangle right here, then of this triangle right here, the longer side is there because it's across from the obtuse angle. That makes OR less than OQ. So R is inside gamma. And similarly, you pick a point, maybe B outside. Then similarly, scale inequality, you've got the, you must have the OAQ is a right triangle. And so then OQB is an obtuse triangle. And that makes the OB bigger than OQ, which makes B outside gamma. All right. So that scaling inequality from way back became very useful for a lot of things because circles are built on distance. So finally, we have theorem 8.111. If gamma is a circle and L is a line such that L contains a point A that is inside gamma and a point B that is outside gamma, then L is a secant line for gamma. Okay. So this proof is very real analysis, and we don't need to cover it. Okay. It has too much about the nature of the real number line that is better left. It's a very those of you who are taking real analysis will see more proofs like that, but it's not necessary for us to kind of go into that proof. Okay. But the corollary is that if gamma is a circle and L is a line such that L contains a point A that is inside gamma, then L is a secant line for gamma, because basically lines have all these distances, like the 1 corresponds with the real number line. So you have to eventually get a point that's further away than the radius and gets outside the circle. All right. So we're on our last slide here. So two circles, alpha and beta, are tangent if their intersection consists of precisely 1 point. So you could have circles tangent like this, or you could have circles tangent like that. Okay, that's the two ways you might see tangent circles. So our theorem 8.15 is circles gamma 1 and gamma 2 are tangent at P. Then the centers O1 and O2 are distinct, and the 3 points O1, O2, and P are collinear. Furthermore, the circles share a common tangent line at P. Okay, well, so it's got to work for both cases. So there's O1, there's O2, and there's P. So if we kind of do that and do that, and then, well, if P, these two circles are right here, so I can create a tangent line. And actually, the way the proof works, well, let's do the proof like more like this. So we don't need to draw the circles even, because circles are just distances. So I want the center O1 and the center O2 and the point P, and I'm going to draw it weird. And then I'm going to draw the line from O1 to O2. And so maybe I'll try drawing these circles, even though it's going to be weird. Let's do weird. Purple feels like a good weird color. Okay. Oh dear. Okay. Poorly drawn circles, because this is an absurd kind of proof by contradiction. Okay. Then that's too bad. That's even by absurd standards. That's not very good. All right. So there's P. So if we draw O1 to P, and O2 to P. So this theorem came after the theorem about a line that this line O1, O2, this line O1, O2, it contains a point inside this circle, so it's a secant line for gamma 2, and it contains a point inside O1, which is inside gamma 1, so then it's a secant line for gamma 1, which means it must intersect the intersect the circle, each circle twice. Now, it has to intersect the circle twice. So imagine it, if it intersected here and it had maybe like A there and B here. Well, in that case, I would have this. In that case, I'd have a isosceles triangle there, an isosceles triangle there. And where does the absurdity lie? Well, then the absurdity lies in the fact that since this is an isosceles triangle, this angle must be acute. And and these are possibly different lengths, but they're isosceles triangle. And this angle must be acute because that's isosceles triangle, which makes, let's use red here, which makes that angle and this angle obtuse. So I have a triangle with two obtuse angles. That's ridiculous. There's the absurdity. So it can't be that way. Circles have to intersect at P. All right, well, that completes this section.